Hi, everyone. So today we're gonna dive into fractions, our section 1.3. Our learning objectives for today are the following. We'll be able to simplify fractions. We'll be able to multiply, divide, add, and subtract fractions. And then we'll also be able to use our knowledge of order operations, our PEMDAS. Please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, and subtraction. And then last but not least, we'll be able to evaluate variable expressions with fractions. So let's dive into it. We have a definitions slide. What is our formal definition of a fraction? Well, we have a fraction is written in the form A over B, where obviously our B can't be equal to 0, because if it is, then we have a denominator of 0, and that is an undefined value. Something to foreshadow in future lectures is anytime we are looking for a domain of a function and that function happens to be a fraction, we want to make sure that we exclude any values that make that denominator 0. Those are known as restrictions. And then the last part of this definition is just saying the numerator represents that top number, so A, for instance, and the denominator represents that bottom number, B. A fraction represents parts of a whole, and the denominator B is the number of equal parts the whole has been divided into, whereas the numerator indicates how many parts are included. So fractions that have the same value are known as equivalent fractions. And then we'll get into what's known as our equivalent fractions property that I'll highlight in pink below here, which allows us to find equal fractions and gives us the ability to simplify fractions. I put a visual of a representation of a pizza pie off to the right over here, and I shaded in 3 slices, and there are 8 equal slices in total. So to represent that as a fraction, our numerator would be the 3 slices shaded in, and the denominator gives us that whole, the whole number of slices that we're looking at, 3 out of 8. Our formal definition of our equivalent fractions property is the following. Again, I'll highlight this in pink, but we're using just arbitrary values. We'll denote them as variables A, B, and C. And then also, once again, we have to highlight the fact that our denominator cannot be equal to 0. So our restrictions for our B and C value are the fact that they can't equal 0. And so what's happening in this box here? Well, if we have a fraction A over B, and if we multiply it by what we like to call a fancy form of 1, right? We're not manipulating, or we are manipulating this fraction, but we're not changing the value of the fraction. And so when we do that, what we'll get is an equivalent fraction. So any fraction multiplied by a fancy form of 1 is an equivalent fraction to what we started with. And these are just the step-by-step procedure in simplifying a fraction. What's the best way to simplify fractions? You kind of want to look for factor pairs or factors that your numerator and denominator share so that we can pull those out and put it into simplified fraction format. Okay, so let's finally start with our first example. We have example 1 here, and we're asked to simplify negative 315 all divided by 770. So straight off the bat, I know that 5 goes into both of these. Huh. Scary noise from the ceiling. guys probably didn't hear the sound, but it was loud. So it just almost scared me out of my seat. Okay, so we're going to divide both the top and bottom by 5. And so how many times does 5 go into 315? Well, we know 10 goes in 31.5 times. So 5 goes in double that. So we have 63. It's negative, so we're going to put a negative 63 in our numerator. And then let's do that same sort of trick with the denominator. 10 goes into 770, 77 times, right? We just moved that imaginary decimal over one to the left. So it goes into 5, double that. So what's double 77? It's just the same as 140 plus 14, which is 154. Okay, and then we ask ourselves again, can we simplify this even further? And the first thing that should really pop into your head is, are the top and bottom both divisible by 3? We know the top is, but is the bottom, and the bottom actually is not. So we have simplified form. There are no other numbers that both 63 and 154 share that same factor. Okay, so we're done. Let's move on to the next slide, which is our second objective, being able to multiply fractions. And multiplication of fractions is the most straightforward out of the 4 operations. All we have to do is, if we have 2 fractions, we put them right next to each other, multiply the numerators, multiply the denominators, you have that new fraction, you simplify that fraction, and you're done. So let's put that into action with this example too. So we're looking at negative 12 over 5, and that's being multiplied by negative 20x. Well, what's negative 20x as a fraction? We just put that all over 1. Technically, we don't even need the parentheses anymore. So we have negative 20x over 1. Now let's multiply straight across. And actually, if we multiply straight across, we're going to be dealing with some larger values, 12 times negative 20, or negative 12 times negative 20, which we can do. That's still not too challenging, but we can make our life a little easier. I see that 5 goes into negative 20x evenly, right? We know 5 goes into 24 times, so 5 goes into negative 20x, a negative 4x times, and 5 goes into 5 once. So now when we multiply straight across, we have much smaller numbers that we're dealing with. Negative 12 times negative 4x is positive 48x. And then our denominator is just 1, so simplified, we can just keep it as positive 48x, and we're done. We have another notes slide, and this is just saying, now that we know how to multiply fractions, now let's look at dividing fractions. And one vocabulary word you should know when it comes to dividing fractions is the reciprocal of a fraction, where you're just flipping the numerator and denominator. A good example is, what's the reciprocal of 2/3? Well, when you flip the numerator and denominator, you simply get 3 over 2. And so when you're dividing fractions, you're sort of utilizing that knowledge of reciprocal, and then we're manipulating this division of fractions to put it into a multiplication problem. So the sort of phrase I like to use is like, to divide by a fraction, here's a trick: keep, change, flip. The keep stands for you're keeping that first fraction exactly the same, not doing anything to it. The change is now you're changing that division symbol to a multiplication. That's where that manipulation comes into play. And then the flip is we're utilizing our knowledge of reciprocal. We are flipping that second fraction. We're putting that numerator into the denominator and that denominator into the numerator. Now we have two fractions that are being multiplied by one another, and it's the same procedure as before. So let's put that into action with our example 3. We're looking at -7/18 divided by -14/27. Keep, change, flip. We're keeping that first fraction exactly the same. We are changing that division sign into multiplication. Again, that's where that manipulation takes place. And then the F, once again, stands for flipping that second fraction. So instead of looking at -14/27, we're now looking at, I'm just going to keep the negative in the numerator. Doesn't matter whether you put it in the numerator or the denominator. And then I have now 14 in the denominator. And then you can multiply straight across. But is there any simplification that can take place before multiplying these higher numbers? Well, I see a 7 in the numerator and a 14 in the denominator. 7 goes into 14 twice, 7 goes into 7 once. And then from the 18 and 27 side, they both share a factor of 3. 3 goes into 18 6 times, and 3 goes into 27, -27, -9 times. And then we can actually pull out another factor, right? 18 and 27 were actually, the highest factor was 9, but if you didn't catch that, with the 6 and 9, you can just pull out another 3. 3 goes into 6 twice, 3 goes into -9, -3 times. And now let's multiply straight across. We have a -1 times a -3 is a +3. And then we have a +2 times a +2 is a +4. So our final simplified fraction is 3/4. And we're done. We have another notes page, complex fraction. So a complex fraction is a fraction in which the numerator or denominator contains a fraction. And you'll be seeing this a lot throughout this course, as well as pre-calculus. Maybe not so much in calculus, but it pops up a good amount in pre-calc. And so this is an example of a complex fraction just dealing with numbered values, but we'll eventually get to a bunch of expressions in terms of complex fractions. We have a fraction in the numerator, we have a fraction in the denominator. This is where we're really utilizing that knowledge of keep, change, flip. Keep this fraction the same, change this to a multiplication, and then flip this. And then go through the whole procedures of multiplying fractions. So let's solve this example 4. We have a complex fraction, where once again, and I'll use the same colors that we did here. We have pink, yellow, blue. So keep this fraction exactly the same. Change the division sign to multiplication. And then flip that last fraction. So now we're looking at x/2 times 6/xy. Let's see if any simplification can take place. We know 2 goes into 6 3 times, 2 goes into 2 once, and an x divided by an x is just 1. So we're really just looking at 3/y as our final result. We're good. Now we're on to our third objective, being able to learn how to add and subtract fractions. And so we have to add or subtract fractions, they must have a common denominator. And how do we find a common denominator? Well, LCD, your least common denominator, is the same as LCM, your least common multiple. So you can utilize what's known as the cake method. And I'll jump through the whole cake method procedure with you guys again in our next example. This slide is just really formalizing the definition of least common denominator. It's the least common multiple of the denominators that you're looking at. And then this is the step-by-step procedure in adding or subtracting fractions. You find your LCD, you manipulate your original fractions into those equivalent fractions with that LCD, then you add or subtract those numerators, and then you simplify. So, knowing that, let's take a look at example 5 here. And I put in the step-by-step procedures already so that we can just really tackle it really efficiently. So first step, we just want to find the LCD of 12 and 18. So let's use our cake method. We're going to write out 12 and 18, and we're going to draw our first layer of upside down birthday cake. I'll color code the first one so you can really see the cake coming to life. We have a nice blueberry layer here. And then we ask ourselves, okay, what's a number that goes into both 12 and 18? You don't have to choose the highest factor. It helps if you do because it makes your process and your cake smaller and shorter. So you'll figure it out quicker. But let's say you don't know the highest one and you know 3 goes into both. Pull out 3. 3 goes into 12 4 times. 3 goes into 18 6 times. And then we're going to go ahead and draw our next layer of cake. As you are completing each layer of cake, we'll make this a lemon one now, we want to ask ourselves a very important question. And that question is, are these two numbers relatively prime? Well, what does relatively prime mean? Relatively prime is simply being able to find the factors of the two numbers we're looking at. And if those two numbers only share one factor, that factor being the number 1, then we know that the two numbers are relatively prime. We know any two prime numbers will always be relatively prime, but we can have a composite number and a prime number that are relatively prime to one another. In fact, all composite, well, I shouldn't say that, but a lot of composite and prime numbers are usually relatively prime. But sometimes we have a composite number and another composite number that are relatively prime. So we always want to ask ourselves that question. In this case, 4 and 6 aren't because besides 1, they also share a factor of 2. 2 goes into 4 twice, and 2 goes into 6 3 times. We're now on our third layer of cake. Make this a nice little strawberry layer. And we once again ask ourselves the questions, are 2 and 3 relatively prime? In this case, they are. So our nice, beautiful cake is complete. We can add some candles to the top or to the bottom since it's upside down. And we're done. So how do we find that LCM/LCD? Well, we just want to take the product of the boot of this cake. Our greatest common factor is really just the product of the diagonals. So 3 times 2, that gives us 6. Our GCF is actually 6. We don't need that for this problem, but we'll need that later on throughout this course. But the LCM, also known as our LCD, is 6 times those two bottom numbers, times 2 times 3, which gives us 36. And that's the number that we need in order to move on to that second step. So now that we have our LCD, we want to find equivalent fractions, and we want to make sure that both fractions have that same denominator. So that's 7 over 12 that we started with. We want to multiply this by a fancy form of 1 in order to get a denominator of 36. And we have to do that same procedure for 5 over 18. Multiply this by a fancy form of 1 to once again get a denominator of 36. And so 12 times what number gives you 36? 12 times 3. So that first fraction is being multiplied by 3 over 3. So our new numerator is 21. And then 18 times what gives you 36? That's just 2. So we're multiplying that second fraction by 2 over 2. 5 over 2 gives us 10, so that's our new numerator for the second fraction. And now we're ready to move on to that third step, where we are just simply adding those numerators and keeping that denominator. 21 plus 10 gives you 31, and our denominator is 36. And then we ask ourselves, can we simplify this further? And we actually can't. This is in fully simplified form, so we completed the problem. We're done. So to summarize everything, what did we learn? We learned how to multiply fractions, divide fractions, add, and subtract. We didn't look at a subtraction example quite yet, but we will. And then also we practiced our knowledge of finding least common denominators. So let's look at example 6, where now we're involving some variables into our fractions, and we're asked to subtract these two. So once again, let's find a least common denominator between 6 and 10. We know 2 goes into both. 3 and 5 are relatively prime, so our cake is done. We're going to take the product of our boot. So we have 2 times 3 times 5, which gives us 30. That's our least common denominator. Now we want to manipulate these fractions to have that denominator of 30. So we're multiplying by fancy forms of 1, the first by 5 over 5, the second by 3 over 3. And when we do that, we end up with 25x for the first numerator and a negative 9 for the second. This is all over the same denominator of 30, so we can put that all under one fraction now that we're getting the hang of it. And can this be simplified further? It cannot. 25x and 9 are not like terms. So that's it. We completed our part A. Now part B is asking us to just multiply. And so we can look at this once again as one fraction, multiply straight across. But then instead of multiplying straight across and then simplifying, let's see if we can simplify a little bit now. 5 goes into 10 twice, and 5 goes into 5 once. 3 goes into 3 once, and 3 goes into 6 2 times. And now we're looking at 1 times x times 1, which is just x, and 2 times 2, which is just 4. X over 4. And we're done. So now we're into our fourth objective, which is using the order of operations to simplify. And so one sort of thing to note on the bottom here is, I sort of mentioned it before, but the whole placement of the negative sign, these are all equivalent. We can have the negative in the numerator, the denominator, or smack in the middle. I personally like to keep it in the numerator. That's what I'm most comfortable with and what I did when I was your age, but it's up to you where you would like to place it. And again, that fraction bar really acts as a grouping symbol. So whatever's in the numerator, you want to try and simplify to the best of your ability. Same goes for the denominator before we sort of put that whole thing together. And yeah, this box right here is just the step-by-step procedure in simplifying expressions with fraction bars. But let's put this into action. We're once again back to just numbers, and then we'll incorporate some variables. So, utilizing our knowledge of PEMDAS, right? Our whole please excuse my dear Aunt Sally, focus on those parentheses first. We have 4 times -3, which gives us a -12. And then we have a 6 times -2, which gives us also a -12. And I'll color code so that you can see what pairs with what. And then we have a 3 times, or -3 times a +2, which gives us a -6. Now let's simplify that numerator. -12 plus -12 is a -24. And a -6 minus 2 is a -8. We know 8 goes into 24 3 times, and a negative divided by a negative is a positive, so our final value is just 3. And we're done. How to simplify complex fractions. Again, what I said before, really focus on simplifying that numerator and simplifying that denominator separately, and then use our strategy of keep, change, flip in order to convert that division problem into a multiplication of fractions. And then once you're there, then if you can still simplify a little bit further, then go ahead and do that. So let's look at example 8 for a simplifying problem dealing with complex fractions. We're going to simplify that numerator first. 1/2 in parentheses squared is the same as 1/4. Let's now simplify that denominator. And so 4 plus 3 squared is the same as 4 plus 3 squared over 1. 3 squared is 9, so we're really looking at 4 plus 9 over 1, and 4 plus 9 is just 13. So we really have 1/4 divided by 13 over 1. Now we can go ahead and convert this division problem to a multiplication using our whole keep, change, flip. We are going to keep the first fraction exactly the same. We are going to change that division to multiplication. And then we are going to flip that 13 over 1, so we're now looking at 1/13. And now let's multiply straight across. We have 1 times 1, which is 1. And 4 times 13 gives us 52. So our final result is just 1/52. And that's it. Let's do another complex fraction example together. Again, we want to simplify that numerator first, and then we want to simplify that denominator next, and then go through the whole procedure of keep, change, flip. In the numerator, we are adding fractions, and in the denominator, we're subtracting. So we're going to have to use some common denominators here. Now, 2 and 3 are relatively prime, which means we can just multiply that first fraction by 3/3, since our LCD is just the product of 2 and 3, which is 6. And we can multiply that second fraction by 2/2. When we do that, we're looking at 3 plus 4 all over 6 for our numerator. Now, in our denominator, 4 and 6 are not relatively prime. We can pull out a 2 from both. Notice how I'm doing cake method off to the side. And then we get to 2 and 3, which are relatively prime. So we just take the product of 2, 2, and 3, which gives us 12, which is our LCD. So we're going to multiply 3/4 by 3/3 to get that denominator of 12. And 1/6 by 2/2. So we're looking at the fraction 9 minus 2 all over 12 in our denominator. Let's just simplify those yellow and blues one last time. 3 plus 4 is just 7. So we have 7 over 6 in our numerator. And 9 minus 2 is 7. So we have 7 over 12 in our denominator. So now we're at the point where we can utilize our keep, change, flip. We are going to keep that first fraction exactly the same. We are changing that division sign into multiplication. And then we are flipping that denominator to now become 12 over 7. When we multiply across, we notice 7 goes into 7 once and 7 goes into 7 once. So we can simplify that before multiplying straight across. And 6 and 12 share that factor of 6. 6 goes into 6 once and 6 goes into 12 twice. So we're really looking at 1 times 2 in our numerator, which is 2, and 1 times 1 in our denominator, which is 1, which just fully simplifies to our value of 2 in the end. And that's it. We're finally on to our 5th objective and our last one for today, which is being able to evaluate variable expressions with fractions. And so in this circumstance, or in this bullet point, what we're doing is wherever you see a variable, if you're given what that variable is valued at, you just plug it in. Use your order of operations to simplify and find that simplified version of your expression. So let's look at example 10 together. We have 2x squared times y, and we're given that x is equal to 1/4 and y is equal to negative 2/3. So wherever you see an x, let's draw some parentheses. And wherever you see a y, let's also draw some parentheses. The x we're going to color code to be pink, and the y we're going to color code to be yellow. And our x is just 1/4. Our y is negative 2/3, which is just negative 2 over 3. And now let's use our order of operations to simplify further. See some parentheses and exponents. 1/4 in parentheses squared is just 1 over 16. 2 as a fraction is just 2 over 1. And then we have this whole negative 2/3. We're just multiplying straight across at this point, but let's see if we can simplify a little bit. We know 2 goes into 2 one time, and 2 goes into 16, 8. And we know that 2 goes into 2 one time, and 2 goes into 8, 4. So when we multiply this across, our numerators are 1 times 1 times negative 1, which is a negative 1. And our denominators are 1 times 4 times 3, which is just a positive 12. So our final result is negative 1 over 12. And we're done. And so this completes our section 1.3. I hope this was helpful. Next time we'll be learning about our section 1.5. Let me know if you guys have any questions, and have a great rest of your day. Take care.